All right, everybody. Justin Robinson is out of town, so they left the sound guy in charge. My name is Zach. I'm a grad student at Georgia State, and welcome to Astronomy on Tap. Woo! So this week we have Nabanita Das, who's a PhD candidate here at Georgia State. She studies black hole. She's a good friend of mine. And she went to Presidency University, which is like the Ivy League of India. Um, and she came here, and now she works on black holes, and she's going to tell us all about how to weigh a black hole. So, Nabo, whenever you're ready.
Thank you. Hello, hello. Is this on?
Yes.
Okay. Is the recording on?
Yes.
Okay. Hi, everyone. I'm excited to talk about black holes, and thanks to Zach for that very kind introduction. I am Nabanita. That's a long and multi-syllable name, so you can call me Nabo if you have a question. And I study black holes, so I am super excited to talk to you about it. All right, let's get started. So, first things first, what are black holes? What is a black hole? In the animation here, you would see some tiny black birds popping up out of the space, kind of come from nowhere. That is an exact depiction of what black holes behave like because we can't actually see them. They're invisible, but they are out there in space. So how do we define that? Is we say black holes are basically regions of space where even light cannot escape from because of its very, very strong gravity. That's basic, and we know that. So now let's move on to how do we make a black hole? And here's a recipe for you. You can try. Um, we're going to start with an entire planet. Let's just pick Earth. And next step is the most crucial step, also only step, is you're gonna have to squeeze it down to the size of a single peanut. Be careful, you're not allowed to lose any percent of the mass in this squeezing procedure. If you lose mass, then you're gonna have to squeeze this harder to make even smaller size. So if you can do that, voila, congratulations, you have made your Earth mass black hole or a peanut-sized black hole that contains entire mass of our planet into a peanut. Is that how we do things in space? Not quite. Now, we don't make black holes. We do be looking for them, and we're going to talk about where we can find them. So the first one is in stellar graveyard. There are different types of black hole, and the first one we find them in stellar graveyards. These are called stellar mass black holes because the total mass of the black hole is always less than the mass of 100 suns put together. What do I mean by stellar graveyard though? So when stars form, they are just giant balls of gases, kind of like this. If it's a low mass star, when its fuel empties and it doesn't have any more gas to burn, it kind of ends in life. Before that, it pops up and ultimately becomes this tiny thing called white dwarf. Now, if it's a slightly larger mass star, it's a slightly bigger star, then they're going to pop up even more, and eventually they will become a neutron star. But if we have a very large mass star, if we have a huge giant star, when it pops up really well and it becomes a giant, a supergiant, it actually explodes and it emits all the outer layers. It shades all of its outer layers before becoming a singularity or a black hole. So we could say that it's in the fate of, the stars that we see a stellar mass black hole. Um, Next up, we have intermediate mass black hole, which, as the name suggests, would talk about black holes that are intermediate mass, which goes from 100 times the mass of the sun to 100,000 times the mass of the sun. And we have not actually found any of these black holes yet, but the leading theory tells us that they're most likely to be found in these dense clouds of stars. These clouds of stars are really, really dense, and they're mostly old, dead stars, not dead stars, but very close to the end of their life kind of stars. They're stuck together by a huge gravitational pull, and maybe a black hole is just hiding there, lurking there, waiting to be found. Who knows? Last but not least is supermassive black holes, my favorite because they are my bread and butter. These are found in the centers of every galaxies. And it is believed that there is at least one black hole at the center of each galaxy that we see here out in the universe. They are really massive, as the name suggests. They can go from 100,000 times the mass of the sun to about 10 billion times the mass of the sun. And this is a simulated image of what that may look like. Now, you can already see how black holes are classified according to their masses. So, mass is an inherent property of black holes, and it must be really, really important for us to know the black holes. But how do we calculate the mass of something that we don't even see? We cannot just put it on a weighing scale and let it be, right? So, there are some other properties, other tools, kind of like going around a path to get to the mass of black hole. But the most important thing here is gravity. So gravity is always at play whenever we're talking about a black hole. But we're going to talk about a simple example of gravity with things that we know mostly of. So the sun and our planet Earth. Our planet Earth is revolving around the sun at a constant speed of 30 kilometers per second. If we put that into other units, it's about 66,000 miles per hour, insane and illegal speed limit. But the Earth is at space, so who's going to stop? Well, the sun kind of does, because the masses of the sun and Earth is constant. The Earth can actually maintain the speed and to revolve around the sun. But if sun were to grow more massive or grow more bigger, it would have more gravity towards the Earth, towards everything around it, also towards the Earth, pulling Earth towards itself into a spiral path. So the Earth's orbit or Earth's motion would not be stable anymore, and we probably would not be living. On the other side, if sun shrinks down to a little star and it's less massive, then what happens? Then, for Earth to maintain a stable orbit, it actually has to move further away. And it has to actually move slower because now the orbital period is much more bigger because it is outside. So you can already see that if we know the velocity or the speed at what Earth is orbiting the sun and how far it is from the sun, these two things are connected to the mass of the sun. And this is the key point of my entire talk, basically. This is the science that scientists use to determine mass of black holes, because these are the tools that we see not from Earth and Sun system, not simplified as that, but kind of similar. All right, let's look at some examples. So the smaller black holes that I was talking about are the stellar mass black holes. Here is another artist impression of that. This is a black hole, it's its binary partner. These are often found in binaries. Often they're lurking around with another partner. And if we know the velocity of this binary companion or its distance or both, then we can estimate the mass of the black hole. Now, what are these binary candidates? It can be another star, and these cute animations are from NASA Goddard. It can be another white dwarf, or it can be another neutron star. And you can already see the neutron star is kind of wonky and it's like spinning around itself. Now, if you remember, white dwarfs and neutron stars are the two candidates which were also partnered in the stellar graveyard. These are also end products of star life. So what happens is that when these kind of systems are found in space, they produce gravitational waves, and we can detect them and we can estimate the mass of the black hole and many more stuff. Moving on to supermassive black holes. This is one of the most scientifically accurate impression of a supermassive black hole. Can anybody want to take a guess what this black hole is called or where it is from? It is the interstellar black hole. It is Gargantua. Sorry, that was like over a decade ago, but it's it's also my favorite space movie, and they have a really, really, really good impression. So it's gonna be up there. Yeah, so from moving on from film references to real life, we start with our favorite black hole at the center of our own galaxy, Milky Way, Sagittarius A star. And we're going to talk about how we measure the weight slash mass of the black hole of Sagittarius star. Here, I'm showing you an animation of, come on, of observation that were taken from the stars moving around the black hole, which is denoted by a star sign. Um, so just bear with me. So the star here is the black hole, and all the circles here are actually stars. And these observations were taken by the UCLA Galactic Center group using the beautiful Keck telescope. Over here, you will see years going around. So they have been taking observations since the 1990s, and I think they're still going on. It's a multi-decade observation. And even after that, let me play that again. Oopsie. Oopsie. Come on. Come on. Okay. Even after that, you would see that some of the orbits of the stars are not enclosed. So what is going on? I want you to look at this yellow orbit right here from this star, which is the closest to the black hole. This star is called SO2, and it takes about roughly 20 years to completely go around one time around the black hole. Its orbit size is really small. It's only 4 times the size of our solar system. Now, you may say our solar system is already large. What are you talking about? But these stars are already very, very massive and very heavy. And the speed at what the star is moving is 17 million miles per hour. So, for that speed to be maintained within this tiny region, there was no other object that we know of in physics that could satisfy the criteria for the star to be moving so fast in such short space. So this was a direct proof, this was an instrumental proof of the fact that in fact our galactic center harbors a supermassive black hole. And they also gave us a number. Its mass is only 4 million times the mass of our sun. Only. And this is not even the most massive black hole. We will talk about that more. But since this was a big big discovery, and a huge milestone for astronomers, this actually gave the scientists a huge recognition back in 2020. Reinhard Genzel and Andrea Ghez shared half the prize for discovering the observational proof of black hole. And Professor Andrea Ghez here, she is the lead of the group from UCLA that did the 30-year-long observation. Half the prize went to Roger Penrose, and he contributed more from the theoretical side for our understanding of black hole, but these two people were the observational scientists. Okay, so that's it. Now you know. You look at stars and you determine how massive the black hole would be because you know how close the stars are orbiting. Yeah. Because the space, our universe is really, really empty. There is so much empty space. Things are there, but everything is so, so, so far away. To put things into perspective, here is an image of our own galaxy, Milky Way. You see the central supermassive black hole, you see the location of the sun pointed by the yellow arrow. Now, the distance between the center to us or to sun is 8 kiloparsec. Parsec is a unit of distance that astronomers use because most of the distances in astronomy is so big. It just means a huge number. To put that into perspective, 1 parsec is 2 followed by 13 zeros miles. I don't know how to say that, sorry. Um, so we're going to talk about parsecs instead. But 8 kiloparsec, the distance between sun and the galactic center, is actually 16, followed by 16 zeros in miles. So that's a huge number. But if you think that's big, let's talk about other galaxies. So the distance between Milky Way and our neighbor Andromeda galaxy is actually 800 kiloparsec, which is 100 times larger than the distance between sun and the galactic center. So there is no way we can possibly think of resolving the center of Andromeda to do the measurement that Dr. Case's group did for Milky Way. And that is only our nearest neighbor. So this is crazy. So how do we even know the masses of other supermassive black holes? Well, we study their environments. So supermassive black holes are known to be influencers. They influence their environments in a huge way. This is a simulation of a moving galaxy center, and you'd see that there are glowing dots. All of them are stars or star cluster, and then there are these thick dust lanes, which are kind of like hazy black lanes. So we can actually study the stars. We can also study the gas and the dust, and all of these are kind of governed by the gravity of the supermassive black hole, so they can tell about the mass of the supermassive black hole. Furthermore, if we zoom into the center and if we can see if the black hole is actually active or eating matter currently, in science, there's a fancy term for that. We call it accretion, but it's just literally gobbling material down into a black hole. Um, that process actually creates these beautiful structures of disks and these jets coming out of the black hole. And this is a whole another realm of very interesting, very complicated physics. But that can also tell us a lot about the black hole's mass and other properties. So we're going to go through each one of them one by one. But how do we do that? So at the end, we always will go back to our Earth Sun system, and we need the velocities of these orbiting bodies around the black hole to measure its own mass. And how do we do it? Well, we use the logic of Doppler shift. So imagine you're just standing at the roadside, and there's an ambulance or fire truck approaching you. So as the fire truck will come towards you, you will hear more intensity of the sound coming from it. But if you were to be standing on the other side of the road and the truck was going away from you, then you would actually hear less and less noise as it was going farther away. So moving sources of sound creates this effect called Doppler effect, where if it's coming at you, it's going to give you high frequency sound. If it's going away from you, it's going to give you low frequency sound. Thankfully for us, light also follows this principle. And in the same way, if a source of light is coming at us, we're going to see high frequency light. And if it's moving away from us, we're going to see low frequency of light. Kind of like this animation right here. And lower frequency light means redder light from our electromagnetic spectrum, and higher frequency of light means bluer light. So when something is coming at us and it's emitting light, it's going to look bluer. When it's going away from us, emitting light, it's going to look redder. Moreover, light or electromagnetic spectra is even more useful because they come in different colors. And by colors, I not only mean all the colors of the rainbow, but also other wavelengths and energy scales of electromagnetic spectrum, starting from radio to X-ray and gamma rays. All these images are of our own galaxy Milky Way, taken by different cameras or different telescopes. We're starting from radio, where some of the gas lanes are glowing, through visible light, where we see the actual image of the galaxy that we know of. Then if we go to higher and higher energy, only the very strong sources of energy are glowing, and we can only see them. This is very useful because The environment of black holes, they not only glow in visible light, but they also glow in different other lights, and we need to detect them to be able to actually determine the mass. Let's talk about examples now. Enough setting up of stage. Okay, here I present to you a nearby galaxy called MCG 63015, which is a huge name. So we're just going to call it MCG. And we're going to study the motion of the stars as a bulk from this galaxy because we cannot resolve individual stars anymore. Not a problem. So we see this disk or this hazy region of light. Most of the stars are right here. And some of them are coming at us. Some of them are moving away from us. This gives us blue shift and red shift. How do we know that? Well, you can't really tell that from this visible light image here, but if we study the stars using other lights such as infrared, using the one and only best infrared telescope out of space, James Webb Space Telescope, of course, um, we're gonna actually be able to see how fast the stars are moving. Moreover, there are also some buddies of ours here on ground, like the Very Large Telescope, that can also study these stars. Side note, astronomers are really bad at naming things. You can tell black hole, very large telescope. Very large telescope is called very large telescope because it's larger than the large telescope. And there is another one planned which will be called overwhelmingly large telescope because it's going to be larger than the very large telescope. So, great. I love this. Anyway, coming back to the science. So, what do these telescopes actually tell us about the motions of the stars? They measure the bulk velocity of the stars, not individual, and they also give us the location of the stars. Both of this putting together, we can create a two-dimensional map of how the velocity of the stars look like. And this is going to look something like this. It's a pretty condensed plot, so I'm going to break this down as much as I can. You see blue shift on this side. So all the stars from this side are actually blue shifted or coming towards you. This side is being red shifted, which means the stars here are going away from you. So in total, you have a circular like motion where the stars are coming at you, going away from you. Now, this two-dimensional map is very, very useful because it has both velocity and the distance of the stars from the black hole. And those are the two things that we needed to measure the mass of the black hole, right? That's it, done. This is actually one of the most widely used techniques for measuring the weight or mass of supermassive black holes. But sometimes we're just not so lucky. Instead, we're left with a galaxy that looks like this, where you don't really see the stars anymore. There is this thick cloud which is hiding all the stars behind itself, and it looks cold and boring, and there is no signature. So, what do we do? Also, is it real? It is real. Um, so here is another friend, NGC 3258, another nearby galaxy. If we look at this galaxy using the legendary Hubble Space Telescope, another best space telescope that we have ever sent to the space, it's going to look something like this. Where you see the glowing center, but you see this very thick dust layer or cloud of gas, and you can't really take observation of stars anymore. So how will you possibly get the velocities that you need to measure the black hole mass? Well, to our rescue, we have this beautiful array of telescope down at the Atacama Desert of Chile. This is called Atacama Large Millimeter Array, and they actually look at the galaxy using radio waves instead of visible light. And what does it give us? it gives us the similar pattern as we saw from the stars. The gas also moves in a circular pattern for this galaxy, where you see blue shift or gas coming towards you, and red shift or gas moving away from you. And you also have a 2D map, meaning you have both the distance and the velocity, and therefore you can estimate the mass of the black hole. So this is all great. But I kept saying these are nearby galaxies. So there has to be something about farther galaxies, right? By nearby, I mean the galaxies in which we can actually see the center of it using some of our telescopes. But there are many, 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 many more galaxies which are millions of parsecs away from us, or even more than that. This is a deep field image from James Webb again. And every dot here that does not have this spider legged structure is an individual galaxy. And as I have said before, we believe that every galaxy hosts a supermassive black hole. So there are millions of galaxies out there in the universe and millions of black holes waiting for us to have their masses measured. Not really. Um, how do we do that? How do we nail this problem down? Thankfully for us, farther away galaxies have a special kind of black hole. Not all of them, but actually most of them. They are active. They're accreting matter, or they're gobbling down material continuously, and therefore creating these structure around them. This is a special kind of environment, and I call them active galactic nuclei, because the black hole is active, and this is the nucleus of a galaxy. Um, matter actually falls down into the black hole in this disk-like structure that we call the accretion disk. And in this process of falling down onto the black hole, there is actually a lot of friction going on into the matter, because they are moving really, really fast, moving down to the black hole itself. So that creates ripples or waves. And we can study waves. We can just set out a detector that detects waves for as long as we want. We don't need to have a high resolution camera to study waves. And if the waves have some structures or ripples in them, and we study them for long enough and we see some pattern matching, then we can probably get more info about the black hole. Something that we already do with like studying this kind of ripples is electrocardiogram or ECG, where we study the ripples generated in our own bodies. And doctors can tell us if there's any anomaly in the signals, and we can test ourselves, right? But for black holes, they don't actually have a heart that beats and that creates ECG, but they do have these ripples, and they have really hot gas outside of this falling material, because this process is really, really, it's really messy, and it heats up entire environment around it. So those gases actually create echo that can tell us about the mass of the black hole. How do we do that? Well, let's just take the simple example of echo. So you are standing close to a mountain and you scream at it, and it screams back at you. And you measure how long it took for the scream to get back to you. Now, your friend is just standing in front of all of this. They're just there to take a cool selfie of you and you're screaming at the mountain. So they noted the time very precisely. Now you know the time, and you know how fast sound wave moves. So if you know the speed of sound and you know the time, you can actually calculate how far the mountain is from you, which is just velocity times the time, right? The same principle can be applied to the supermassive black holes that have glowing and really hot ionized gas clouds that echoes the same principle from the disk. How does that happen? So here's a teeny tiny black hole minding its own business, eating material through the accretion disk. You're out there pointing a telescope at it, and it shoots a ripple at your telescope. At the same time, There are hot ionized gas around the black hole. And the moment it shoots the ripple at you, it also shoots the ripple at every cloud because signal is isotropic, right? It cannot just detect your own telescope. Now, this gas is so hot that it actually then echoes the same signature and reflect the same signature to your telescope after a certain time. That is the same time that photons take or light particles take to go from the disk to this cloud. Now, if you can detect the time, if you can measure the time delay between these two signals, and you know the speed of light, you can detect how far these ionized hot clouds are from the supermassive black hole. And that is the essence of something called reverberation mapping. It's a huge name. But that's one of the most used techniques for any black hole that is farther away from us, and we cannot study its center by looking at the stars or the gas. Um, now, these are now, these are all the techniques that we study for the environment of the black hole. What about the black hole themselves? Have we actually looked at it? Well, we have. Oops, sorry. We have with the Event Horizon Telescope Network. This is a network of telescopes located at different locations of our planet Earth, and together they create an effective telescope that is as big as the entire planet. So they have a baseline as big as Earth, and they look at distant black holes trying to take their images. This is one of the black hole images that they took of a nearby supermassive black hole, M87. You can see the accretion disk glowing around it. It's not really accretion disk, it's some signature of accretion disk. And then the black hole is lying here. We did not forget our own guy, Sagittarius Star, and we also took a picture of Sagittarius Star. Now, you may think that these two pictures look kind of the same but not similar. Are they different? Well, they are, because M87 is active. Our galaxy does not have an active black hole. And also, Sagittarius Star is much more smaller compared to M87. In fact, now we're going to look at a video from NASA that compares the masses of supermassive black hole, comparing that to, oops, oh, sorry, comparing that to the solar system size. You can play. Thank you. Okay, so that's the sun. And we already have a black hole lurking within the orbit of Mercury, that is a supermassive black hole. So you can imagine how much dense the environment would be, because this is a really tiny space for millions of solar masses to stay in. And now we're past the orbit of Mercury. I'm gonna take a sip of water and let you watch. All right, so here comes our Sagittarius star, which is about the size of the orbit of Jupiter. And then a little bit farther away and a little bit bigger than Sagittarius star is the black hole at the center of Andromeda. Oops, right here. And then we're gonna see how massive M87 actually is. And finally, we have the really giant supermassive black hole, TON 618. This black hole weighs about 66 billion times the mass of our sun. And this is, I think, on record, is the biggest black hole that we have detected so far. Um, okay, so that's all from me. Black holes are mysterious, enigmatic, they are hiding, but it's so cool to study them. But you know what's cooler? Is building a telescope. Okay, so here's an announcement for next week's Astronomy on Tap. Um, Our newly graduated Dr. Fallon Kono will talk about how to build a telescope starting from the screws themselves that they use to observe the sun. And with that, thank you everyone for your kind attention. I can take any questions.
Thank you, Nava. We have some QR codes. We have our website and our Instagram if you want to keep up with what's happening at Astronomy on Tap. And then we also have a Venmo here where you can tip, and all of the proceeds from this go directly towards helping grad students publish papers, helping them travel to conferences. It's very helpful for us. But yeah, does anyone have any questions for Nava?
There's someone there.
Ah.
Yeah, great talk. I was wondering if these black holes are taking stuff into them, are they then growing? Is the mass growing and they keep getting bigger and bigger and bigger till they're super massive?
For the first part of your question, are they growing? Yes, they're growing. Actually, we can calculate how much black holes have grown over the time. Like the supermassive black holes have grown over the time, and we can use that proxy to estimate the age of the universe to see like how much matter they're accreting over the years and how much more masses they're gaining. But can they grow into from a stellar mass black hole to a supermassive? Probably not. They cannot engulf so much matter that they can completely jump the mass segments and become supermassive, even from intermediate mass, I believe. Thank you.
I think there was another question. Yeah.
So you brought up the three different types of stars there was. And
Mhm.
the one that creates the black holes, is there like a measurement type of the strength released when that is created, like the pressure given off or something like that?
Are you talking about when the explosion happens? Is there a pressure that creates?
Yeah, like can you measure that strength, which is what's released from that?
I believe is it relativistic? Stellar people can back me up here. When supernova explosion happens, is it shooting material at relativistic speed? Okay. Yeah. So, but I think when the explosion happens, all the outer layer gets ejected out at a relativistic speed, but it's the core that is remaining that cannot hold its own gravity anymore in the form of an object that creates the singularity or black hole. Thank you.
Any other questions? I have one. What's a black hole that you have measured or weighed? Because that's your whole gig, right?
That's the black hole in the center of MCG, but yeah. So we didn't put a mass label on it, but we're working on it. We have measured the mass of MCG using two different techniques, and they're kind of wonky right now. So follow me for the next AOT talk. We'll talk about it.
Breaking astronomy at Astronomy on Tap. Any other questions? If not, feel free to come on down and talk to Nava. It's cloudy as shit outside, so we can't really see anything. We were gonna look at Jupiter, but it's hiding. But let's thank Nava once again. Thank you all for coming out. Please remember to tip your bartenders, and we'll be hanging around. Thanks, all.